Okay, now let's apply those principles of the potential energy to the electric force. Let's first assume that we have a single charge, Q1. And we take some other charge, let's call it Q2. Initially at this point, we just fix that charge Q1 over there. This is the charge Q2, initially at that point, and then we move it to this point. Let's say this is the point P0, this is the point P. Along a path given by this one. Now we can do this. And let's just assume that we are not giving it any acceleration. We are moving this with constant speed. Or initially, if it was at rest, we are moving it so slowly that its speed is almost always 0. What should be the force that we should exert on it? That we should be exerting on it? Let's see, at this point, the force acting on the charge Q2 will be 1 over 4 pi epsilon 0, Q1, Q2 divided by r squared in the r hat direction. This is the force as the charge is moving, it will reach this point, and at this point, this is the force that this other charge will be exerting on this one. And we are moving this object with 0 acceleration, so what should be the force that we are exerting on it? Now, if we are exerting 0 force on this object, then this will be the net force acting on this object, and dividing by this net force by the mass of the object, we will get that it has a non-zero acceleration. So we should be exerting some force on this object. Well, if we want 0 acceleration, the net force should be 0. So the force that we are exerting should be minus this one. With 0 acceleration. It's moving, but 0 acceleration. And 0 speed. Well, it's moving so slowly that it takes infinitely long to reach this point. Well, the work will not depend on time because the force doesn't depend on time. So the work that we do as we move this object from P0 to P would be just minus F. This is the force that we are exerting, dot dl, integrated from from P0 up to P. This is the work that we had done. And we interpret this work as some energy, some concept stored in the system. So initially, my system had this potential energy, initial energy, let's say U of P0. Then I do work on the system. This is the work that I have done. So I have stored some more energy in the system, this one. So the total energy stored in the system became its initial energy plus the amount of work that I have done. This is why we have this minus sign in the definition. It is the amount, in fact, with this minus 1, this is the work that some external force should do on the system so as to increase the potential energy of my system. Because this is the force that I have to exert to move my system from here to here with 0 acceleration and 0 speed. Now let's calculate that one. Now we already know that although I have taken my object, my charge from here to this point along this path, I know that the electric force is a conservative force. So it doesn't make any difference which path I took. I could have as well chosen some other path. to go from here to there. The same thing. Or I could have chosen, let's say, this path. Let's say this point is C. And that first segment is a straight line that goes towards Q1. And this other one is an arc. This has radius R. So I first go straight towards Q1. I took my charge from this point straight towards Q1 until I reach the same distance as this point from Q1, and then I move along this arc. Now, the nice thing about this choice is that as I move along this arc, the force is always in the radial direction. But my small displacements are always perpendicular to the radial direction. So along this arc, I won't be doing any work. I only do work along this straight line, and also along this straight line, the angle between, I mean, you see, we define the work as some kind of a scalar product. I have to know the angle between the force and this dl. Along this path, that angle constantly changes. At each segment, I have a different angle. So it will be quite difficult to calculate it. But along this path, the angle is either 0 or infinity, or 0 or 180 degrees, depending on whether the force is pointing, whether they have opposite charges or the same charge. So it will be easier to calculate this integral along this path than along this one. Along this path, the contribution is 0 anyway. Agree? Okay, so let's see. I can write the u of p. This is equal to the integral from p0 up to c of f dot dl plus from c to p of minus f dot dl plus u of p0. Instead of going along this path, now I'm going first from here to C, from P0 up to C, and then from C to the final point, C to the final point. But I already said that this one is equal to 0, because along this line, along this arc, F is always perpendicular to dl. And the only thing left to calculate is this one. Now let's see F. I can just imagine such a path over here. At this segment, the force F will be nothing but 1 over 4 pi epsilon 0, Q1, Q2, divided by r squared in the r hat. And dl will be dl in the r hat direction. Is dl positive or negative? dl. It should be negative, because I'm moving in this direction, so dl is pointing in the minus r hat direction. That means that my dl, this dl number, is a negative number. It will be important later on, because when I determine the limits, since dl is negative, I should be starting from the distance of this one until this one. Now, what is f dot dl? Sure, the direction is negative r hat. But if you take a unit vector, multiply it, if you take any vector, multiply it by a negative number, you obtain a vector whose direction is in the opposite direction. Now, f dot dl is 1 over 4 pi epsilon 0, q1, q2 over r squared times dl. Now I have to sum them all up. Integral of f dot dl from, let's say, R0 up to the final point R is equal to from R0 up to the, let's say, RF of 1 over 4 pi epsilon 0 Q1, Q2 over R squared. No, not DL. DL is DR. No, okay, DL, sorry. Now I have to relate DL by and DR. DL will be, let's say, DR. So this is equal to, if we take the integral 1 over 4 pi epsilon 0 Q1, Q2 times minus 1 over R. This is the integral of 1 over R squared. Evaluated from R is equal to R0 to R is equal to R final. This will be minus 1 over 4 pi epsilon 0 Q1, Q2 over R final plus 1 over 4 pi epsilon 0 Q1, Q2 divided by R0. So I can write the potential energy at the point P minus 1 over 4 pi epsilon 0 Q1, Q2 over R final plus 1 over 4 pi epsilon 0 Q1, Q2 over R0 plus U of P0. Now I am free to choose one value for the potential. I can fix the value of my potential at an arbitrary point. Then that will determine all the values of my potential at any other point. If you want, you can choose U of P0 to be 0, and this will be your potential energy expression. It's a valid, it's a correct expression. Or if you want, you can choose, this is a choice, choose U of P0 is equal to minus 1 over 4 pi epsilon 0 Q1, Q2 over R0. If you make this choice, then we know the potential energy of the system, U of R, is equal to minus 1 over 4 pi epsilon 0 Q1, Q2 over R. Is this correct? Hmm? Do you agree with this one?
So that it be RF?
It should be R what?
F, final.
Well, I just renamed R final to be R. You agree? Let's look at what this tells me. Now, if you remember, for a given system, the system always behaves in the way that the potential energy of the forces will be always in the directions to minimize the potential energy. Let's draw the potential energy diagram. U of R is a function of R, assuming Q1 times Q2 is larger than 0. So we have same charges. This is positive, so this is just a constant. So it's minus 1 over R. The plot of minus 1 over R is this one. So the forces will basically try to bring the charges together. So this minus sign tells me that if I have Q1 and the product of Q1 times Q2 is larger than 0, then the force is attractive. So this is what this potential energy expression tells me. Well, that's not correct. We did a mistake somewhere. Where was the mistake? Where? Which signs? Here. Well, what do we know? We know this vector, the direction of this vector. You see, this dl vector is pointing in that direction. R hat vector is pointing in this direction. Okay? So, dl vector and r vector, they are pointing in opposite directions. So, if I'm going to write the dl vector as dl some number multiplied by the r hat vector, this is pointing in the opposite direction, but that tells me that dl over here should be negative. So that's why we say dl is negative. So where is the mistake? F is in this direction. Which one? F?
Yes.
Why?
Because it is details minus 0.
No, the F, this is the force F, it's plus, because this tells me that if Q1 and Q2, they are the same charge, the force is in the plus r hat direction. So it's pushing, the charges are pushing away from each other. So this is correct. F dot dl is this one, that is also correct. Then the integral of f dot dl is again this one. But of course, I forgot the minus sign over here. This is plus. This is minus because the u of p is minus f dot dl integral. Here this is plus. Here this is plus. Well, you see, in your exams also, most of the time, you don't think what your answers are. I mean, you see, the sign I had forgotten is this minus sign over here. This is the minus sign. There's a minus sign in the definition. So I have evaluated this integral, and I obtain this number, this expression. U of p is minus this one plus u of p0. That minus is the minus I forgot. And by just looking at what my final answer tells me, okay, this is the result, okay, this is a mathematical expression, but what does it tell me? Once you interpret the answer, you see that there is something wrong there. And now let's see if our previous arguments, how did it change? Now, this is not the function. It's like this. This is the shape of my potential energy now, and to minimize the potential energy, R should increase. That is, the two charges should push each other away if Q1 and Q2 is larger than 0. Now, any questions on this one? dl is in that direction. R hat is in that direction. dr is also negative. No. Okay, now you are questioning this expression. Well, you see, you could have said dl is equal to minus dr. That is, you are going in the direction of increasing r in your integral, but in that case, the limits of your integral should start from rf to r0. It should start from the smaller r to the larger one, because if you had put a minus sign over there, then you are defining dr, the change in r, to be positive. Now, you see, you could have chosen dl is equal to minus dr. This is also a valid choice, but this time you are defining dr to be positive, if dr is positive in your sum, you should start from small r to large R. That would change your limits in the integration. So here we had chosen dl is equal to dr, and dr is a negative number. So in the summation, that is in the integration limits, we started from the larger one to the smaller one. Now both of them will be valid, true. Just you have to interpret them properly to determine the limits of your integration. Now, there's one thing that you have to pay attention to, though, in this definition of the potential energy. Now, this is the potential energy of the system. It's not the potential energy of a given charge. In the sense that, okay, this is the energy that is stored in the system, so we can take it away from the system. Now, to take it away from the system, we can, for example, either keep Q1 at rest and let Q2 accelerate away if they have the same charge. So and as it's moving away, accelerating, we can have Q2 do some work, so we are extracting the potential energy stored in the system. Or else we could just fix Q2, let Q1 free, and Q1 will be accelerating away. And as it's accelerating away, we can cause it to do some work, so we will be extracting the potential energy of the system. So the potential energy is not really the potential energy of Q2 or the potential energy of Q1. It is the potential energy of the system as a whole. So that is just one detail to pay attention to. Now let's continue with our example of the potential energy. We had determined that the potential energy, this is the potential energy between two charges separated by a distance r. Let's say we have three charges now. Q1, Q2, and Q3. This distance is R1, this distance is R2, this distance is R3. So what is the potential energy of this system? You can also think of the potential energy of a given system as the amount of work that you have to do to create that system from charges located at infinite distances. So we have these Q1, Q2, and Q3 charges. They are located at infinity, and we are bringing those charges one by one to this final configuration. So how much work we have to do, that is the amount of work stored in the system. That is the amount of potential energy of the system. So let's start with Q1. There is nothing. We bring Q1 to this final point. How much work did we do? How much potential energy did we store in the system as we bring the charge Q1 from infinity to this point? Nothing. There is no force acting on it. We shouldn't exert any force. With infinitesimal force, we can just bring it over here. And then Q1 is already over there. Then we bring Q2. How much work we have to do now? Q1 was already there. And since there was no other charges in the system, when we bring Q1, we didn't do any work. But then we are bringing Q2. We had already evaluated how much work we have to do. It's just our previous expression. This one, 1 over 4 pi epsilon 0, Q1 times Q2 over R1. Now we are bringing Q3. How much work we should do to bring Q3? Well, let's see. Let's first remember our definition of the potential energy. minus F dot dl from A to B plus U0. This was how we had defined. Well, this is basically the work that we have to do. But we know the force acting on Q3 is nothing but the sum of the forces due to Q1 plus the force due to Q2. So this is equal to minus from A to B F1. This is the force due to the Q1 charge minus from A to B F2. This is due to the force due to this Q2 charge. But we have evaluated both of these integrals separately. So we already know that this is nothing but both of them minus. This is equal to 1 over 4 pi epsilon 0 Q2 Q3 divided by R3, no, Q3 Q1. Because this is the work done to overcome the force due to the charge Q1. This is the force acting on Q3 due to Q1. And this is R3. Plus 1 over 4 pi epsilon 0. F2 is the force acting on Q3 due to Q2, so it will be Q2 times Q3 divided by R2. So this is the work that I have to do. That is the amount of potential energy stored in the system if I move Q3 from infinity to this point in the presence of these Q1 and Q2 charges. So that is, again, the energy stored in the system. So the total energy stored in the system would be this one. Q1, Q3 divided by R3 plus 1 over 4 pi epsilon 0, Q2, Q3 divided by R2. Now, you see, if you look at this expression, it's as if, well, I have the potential energy of this two-charge system. It is this one. I have the potential energy between these two charge systems, Q1, Q3 divided by R3. And then I have the potential energy due to these pair, Q2, Q3 divided by R2. So in a sense, the potential energy also has this superposition. You just consider the charges pairwise. Each pair has its potential energy. You just add the potential energies. Now, any questions? Yes.
Now, what is the definition of infinity? I mean,
Very, very far away, in a galaxy far, far away.
galaxy. I mean, these are point charges.
Okay.
I mean, if it's quantum level, so what's the definition of it? I mean, infinity, how it relates here between the charges?
What do you mean?
I mean, Q1, Q3 may be an electron or a proton.
Okay.
So, how we define infinity to be the normal infinity?
Well, in this case, it is really infinity. Very, very far away. Well, in real life, I mean, if you take, let's say, R1 to be 1 kilometer, that is far away enough. That's almost zero, infinity.
So, this is what I mean with a range. We define it is zero for Q.
For R, you mean?
Yes.
I mean, infinity is infinity. Really infinite. I mean, in practical applications, I mean, of course, just, I mean, if you consider the atom, 10 times the size of the atom is far away enough. But in any case, that won't be really relevant. I mean, you can choose infinity to be, I don't know, 10 kilometers. And then, again, this expression would be, the change in the energy would be, again, the same. I mean, you can just imagine these two charges at 10 kilometer separation initially. And then you bring them back here. the expression will be this one plus a very small correction. Other questions? So is this, I mean, whenever you think about the potential energy, just imagine the amount of work that you have to do to bring the system from infinity. Well, why infinity? Because we had defined the potential energy at infinity to be 0. I mean, the amount of work that you do is the change in the potential energy. So if at infinity the potential energy is 0, then the change in the potential energy would be just the final potential energy of the system. Yes?
We said that the potential energy was the difference, the potential energy difference was the work that we needed to do to get from infinity to here. Well, wasn't this work defined as from A to B integral f dot dl itself? Why did we put the minus there?
You see, this is the work done by the force, not by you. By the electric force. Because F is the electric force. Minus F is the force that you are exerting. Yeah, this is all. Other questions?
Just the last step again. Those integrals then
Well, this is what we want to do is the work that we have to do on charge Q3 to bring it from infinity to the final position. Okay? Minus F is the force that we have to exert, so that's why it's the minus F. F is the force that Q1 and Q2 are exerting on Q3. Well, we know the superposition principle for Coulomb's law, which states that if you have many charges exerting force on a single charge, then the force that that single charge feels is nothing but the sum of the forces that each individual charge is exerting on it. So this force F is nothing but the force exerted by the charge Q1 and the force exerted by the charge Q2. But this is nothing but, this integral as a whole is nothing but the work that we have to do if only the charge Q1 was there, without charge Q3. But we had already evaluated it. And this is the work that we had to do if only charge Q2 was there, without the charge Q1. And again, the work that we have to do to bring a point charge to a distance r from another point charge, we had already calculated it. It's this one. So we already know these two integrals, so we just sum them up. Now let's look at one more thing. You see, the force acting on charge Q3 is proportional to the charge of Q3. And in fact, that is how we had defined the electric field. We knew the force. We know that the force is proportional to the charge. So we just factored out that proportionality constant, and what remained was the electric field. If you look at the potential energy, we have the same thing. We have the charge Q3. It's the common. So we can just factor it out. 1 over 4 pi epsilon 0 Q1 over R3 plus 1 over 4 pi epsilon 0 Q2 over R2. This doesn't depend on Q3 anymore. And in fact, this is what we call the potential. At the position of Q3. Now, if you remember the definition of the potential energy, minus F dot dl from P0 to P plus U of P0 So just imagine you are moving one charge around. The force that you are exerting on that single charge is nothing but its charge times the electric field at its position. So the potential energy of the system is nothing but its initial potential energy plus the amount of work that I have to do in order to bring this q prime charge to its final position, which is minus q prime from P0 up to P E dot dl. Now the potential we define as E over q prime. So the potential, electric potential of a point P is defined as, well, you still need to pick up a reference point. You just fix your electric potential at some reference point, minus from that reference point to the final point E dot dl. This is called the electric potential of that point, P. And the relation between the potential energy and the electric potential is similar to, remember, the force is nothing but E over Q prime. The relation is basically identical. If you replace the force in the definition of the potential energy by the electric field, you get what's called the potential energy of that point. No, not the potential energy, but the electric potential of that point. Potential energy, if you just compare the units of potential energy is joules. The unit of potential electric potential is joules per coulomb, what we also call the volt. So if you have a given charge distribution, Qi, let's say, and let's just pick up a point outside of this, somewhere, we can say this point P. Now, if you put a charge at that point, the force that that charge will feel will be Q prime times the electric field at that point. And again, this electric field is the field created by all the other charges. And if you bring that charge, if you put that charge Q prime, the change in the potential energy of the system as a whole will be nothing but Q prime times V of P, the electric potential at that point, again created by all the other charges. Well, the change in the potential energy can be both negative and positive. In Q. U. Well, let's look at this example. It has some potential energy. Now it has a different potential energy, and the change is negative. That's a positive change in the potential energy. You see, if you leave the system to itself, the system will change. If you have some charges, let's say, if you just let the system go, you don't exert any other forces, it's only the forces that the system exerts. And as the charges are moving, they will always move towards smaller potential energy. In fact, going to a smaller potential energy is the natural thing for the system to do. If there is nothing else that is forcing the system to a larger potential energy, the system will always try to go to a smaller potential energy configuration. True. Now there's something subtle. Okay, if you let the system go, let's say we have some charges over here somewhere, and we put some test charge over here. The charges over here are fixed, let's say. These charges are fixed. You put a test charge over here. When you let it go, let it free, it will always move to a point where the potential energy of the system will get smaller and smaller. The potential energy. Now, if it is positively charged, that means if initially it's here, it will move to some other point which has a smaller electrostatic potential, if it's a positive charge. If it's a negative charge, when you let it go to a region which has a larger electrostatic potential. Potential energy always decreases if you leave the system. But the potential, in this case at least, potential for the negative charges increase if you just let them go. Why? Well, of course, that is the consequence of that. But, I mean, we said that if you let the system go, if you release the charge, it will just move to a point which lowers the potential energy. That's always the case. Whatever the force is, the potential energy, when you release the system, it will always try to minimize the potential energy. Because the change in the potential energy will basically go to the kinetic energy of the system. So if initially everything at rest, then you just release it, the kinetic energy increases, so the potential energy should decrease, whatever the system is, whether it's electrostatic, whether it is gravity, whether it's the spring, etc. But you see, this change is negative. If the change in the potential energy is negative, then the change in the V, if Q prime is negative, the change in V should be positive. The potential increases. So the negative charge, it goes to a point which has a larger potential. The potential energy of the system gets smaller, but the negative charge goes to a point which has a larger potential. So that's just one important distinction, let's say, between potential energy and potential. But just keep in mind, potential energy and potential, they are completely different things. They are related, but different.
Why does it do so? Why tend to do?
Well, let's see. The potential energy, as it goes from here to here, we said that the potential energy should get lower. Okay? But the change in the potential energy is, well, remember how we defined it. U is equal to V over Q, no, V times Q prime. Well, this delta U is the work done to bring it from infinity. In general, the potential energy is defined as Q prime times the potential. So delta U, the change in the potential energy as my charge moves from one point to the other one, is equal to Q prime times the change in the potential. This is negative if you just let the system go. If Q prime is negative, that means that it should go to a point such that the change in the potential between those 2 points should be positive. This is negative, this should be positive. If this is positive, the change in the potential of the point at which my charge is positive, then that means V, the potential is increasing. It increased from the initial to the final point.
Why the negative charge specifically tend to go to a higher potential?
Why not?
I mean, not
Because of the definition.
Not mathematically.
Well, you see, the more, let's say, physical concept is the potential energy itself. It's the potential energy that we most of the time measure. The potential energy is always gets smaller if you let the system go. Because of the way we define it, and that the charge can be both positive and negative, If you just let the system go, the potential might be increasing or decreasing. The potential of the point, I mean, the charge might be moving from a point which has a lower potential to a point which has a larger potential if it's a negative charge. It's just like the electric field. You see, negative charges move in the opposite direction of the electric field. And the potential increases in the direction opposite to the electric field. It decreases along the direction of the electric field. And negative charges, they just move in the opposite direction to the electric field. So that's why they go to the points which has a larger potential. Which? This one?
No, no. The graph. Diagram at the top, second row front page. Yeah,
This one, okay.
yeah. Could you take down? You said what will happen if you set the first one and the second one free?
Okay.
What if we release the both of them? Is that free? What will it?
Now, you can release both of them free.
The energy diagram?
Now, you can release both of them free. Both of them will be gaining kinetic energies. You can use that kinetic energy to extract work from the system. And this is the, still, this will be the maximum kinetic energy that they can gain. Both of the sum of them. For example, if you have, let's say, you just release Q2, fix Q1. Q2 will just accelerate. The change in the potential energy will be converted into its kinetic energy. It will have all this potential energy as its kinetic energy. Or you can put fix Q2, let Q1 go. It will be gaining kinetic energy, and this will be the maximum kinetic energy that it can gain. Or you can release both of them. Both of them will be gaining kinetic energies. So the sum of their kinetic energies will have this value when they are infinitely far away from each other. Of course, each one of them will get smaller kinetic energy. But the sum will be this one.
Why do we assume that acceleration and the velocity or the speed are zero? What if it is not zero?
Well, of course, in that case, the work that you do, part of it goes to the potential energy, part of it goes to the kinetic energy. So the reason why we assume zero acceleration is that the kinetic energy shouldn't change. If kinetic energy doesn't change, in that case, the work that you do, all of it goes to the potential energy. Okay, so see you tomorrow.